Good afternoon, everyone. It's exactly 2 o'clock. People are still entering the room. So while we just give them a moment to still connect, I thank you all for your interest in being here. We've had an enormous response to this event. Can someone just maybe show me a hand or something to show that you can hear me? Just so that I know you can hear me. Okay, thank you. You've all been reading the little notice on the side, so thank you for joining the chat. And welcome to this talk that we are having today, showcasing 3 of our doctorate students. One has graduated, Brendon Jones, and then we have 2 that are busy finishing or writing up with their PhD work, Mampho Maoyi and Duan Swart. So the topic broadly today is on the Vadose zone, and one of the University of Pretoria strengths that we are very proud of is our overlap that we have between engineering geology and hydrogeology. So as such, we thought that we'd group together the talks for today to have only the 3 PhD students on this topic to just come and share their ideas. It's a hard topic that we also don't know much of always, so we are very happy about today. Okay. So switch off your microphones, please switch off your video, and please put your name and details in the chat. Okay, so just maybe to give you some context, the Vadose zone, as many or most of you should know by now already, is everything essentially between land surface and the groundwater table. So we focus quite intensely on trying to understand what happens in the zone, to not just simply look at groundwater recharge or surface runoff, but to also look at everything in between. Maybe just quickly, I seem to have some issues with sound. Can someone just in the chat tell me that you can still hear me? I think we have sound issues.
Yes,
thank you so much.
Yeah.
Thank you very, very, very much. Okay, so continuing, this is essentially a simplified model of where we started is, as we all understand, between the surface and the groundwater table, we sit with quite a complex distribution of materials. Part of that is a soil zone in which we have influences of evapotranspiration. There's a lot of work being done there by soil scientists, hydrologists, and more recently hydropedologists, one of the great growing new sciences of earth sciences. And below that, we sit with weathered rock, which is an area of the saprolite or of the subsurface rather that's been neglected quite substantially in terms of specifically unsaturated hydraulics. So we've been looking very specifically at this interface between those. Okay, so what happens here, just a quick intro from my side, is that adhesion becomes more important than cohesion. So wetting of minerals become the process driving movement of moisture rather than only gravity, which is cohesive, which is water molecules clustering together to form heavy drops. So what happens in low saturated state is that water molecules would be primarily still attracted to mineral surfaces, which means we don't have that cohesion, we have the adhesion onto surfaces. And that retards flow, but it doesn't make it zero. And that's something we often miss in this, is the fact that low flow is still flow. But the only thing that's remarkably different in instances where we have low saturation is that gravity is not the preferred direction of movement anymore. So water can suddenly go up or sideways. And that is why we have all these funny flow mechanisms and systems in the unsaturated or Vadose zone. Okay, we sit with funny things that counteract flow, like friction, which is parallel to flow, and inertia, which is usually perpendicular to there, where we have obstacles or energy losses. And as that happens, we retard the movement of water. So there's just a lot of processes that we have to look at. So just a quick intro there. Okay, so today we look at unsaturated mechanics and hydraulics. 15 or 10 minutes a person is not or are not nearly enough, but we will look briefly at rock defects, and we will look at soil, and we will look at that interface between those two. And the idea here is to be less black boxed, less general fluxes, and to move to actually know a rate of movement of a molecule or a drop of water between surface and the subsurface. Okay, So regimes, mechanisms, scenarios, we'll touch on that. You all know of Reynolds numbers, which should be below roughly 10. That's only the start of this. For fractures, it can go into thousands. And then on top of that, we need to look at rotationality. So there's a lot of other things that affect retardation, which make our flow equations less applicable. Okay, so support our researchers. Thank you for being here, Dr. Jones, soon to be Drs. Maoyi and Swart. Thank you to the Water Research Commission who spent a decade on this, and we are absolutely so thankful for them. Thank you to UP. We've established something here that everyone doesn't have in this specific research focus. And please share your thoughts. So for that, thank you also to Gage Consulting and Tel Sullivan and Maley for having your people here together with UP. And with that, I now switch off and I hand over to Brendon. Thank you.
Right, good afternoon, everyone. I just want to check that we are all good here and you can hear me and see my slides.
Yes, we can see you. Oh, we can see you.
Great, and the slides are up.
Yes, you can go. We can see.
Cool, thanks. I must apologize if I'm a little bit slow or don't sound coherent. I'm sitting in Sydney at the moment in Australia, and it's almost midnight here, so my brain may not be functioning optimally. I don't know if it's got anything to do with the beers I had this evening, but we'll give it a go nevertheless. So I was the first lucky student to be involved in this project, working with Matthijs and Louis at the University of Pretoria. And hopefully the aim was always to start off very simple and look at the simple concept of fracture flow. It ended up kind of forming the basis for the rest of the project and Mampho and Duan's research, and really with them sort of advancing it to a much more important stage. So I feel quite honored that looking back at the work that they're doing and how far they've already advanced it. So I'll just give a very brief sort of summary of some of the key findings of my research and maybe some of the applications that we have in fractured rock within the unsaturated zone. So there's obviously many implications of improving our understanding of the unsaturated zone. It's a complex, heterogeneous, and anisotrophic zone within our ground profile, and we need to try and quantify the water movement for engineering purpose, for environmental purposes, for recharge purposes. So there's like Matthijs had mentioned, there's a general sort of consensus to view things as a black box and sort of look at it in this bulk manner. So our project really wanted to move away from that and look at sort of discrete and individual processes. And for that, we had to go back to looking at single fractures at first and then build on that complexity and look at then complicating the geometry of the fracture, complicating the number of the fractures to make the fracture network. So this is really just the basis of it. There's obviously various applications, like I'd mentioned, mining, civil, sort of hydrogeology. And the basis for fluid flow and fractures is governed by the Navier-Stokes equations, the system of differential equations. Now, some of you may know the Navier-Stokes equation. For those of you that don't, it basically describes turbulent flow. It's an equation that describes fluid flow, but it helps us understand fluid flow and turbulence in fluid flow, and not in fluid flow only, but obviously even with gases. So there's various applications. They even use it in climate modeling. So the Navier-Stokes equation is actually one of the millennial problems that the Clay Institute of Mathematics are offering a reward of $1 million to solve the Navier-Stokes equations. So any of you out there have an idea of how to do that, you might have some money up for grabs. So simplifying the Navier-Stokes equation to describe fluid flow through to fractures in natural conditions, we have to oversimplify them. So although in natural fractures they're generally rough and irregular, but for the cubic law we kind of conceptualize a simple model concept of two smooth parallel plates, and we assume that the matrix is impermeable and that saturated laminar flow conditions apply. And from this kind of only very strong simplification of natural conditions, the flux occurring through that single discrete fracture can be determined using the cubic law, which really describes the proportionality of the flux to the third power of the aperture. So that right there is our cubic law. And you can kind of see how we get to that from that natural single fracture, which is complicated with geometries. There's stresses involved in that. So the cubic law really simplifies it to these smooth parallel plates. In terms of flow mechanisms through fractures, we have observed several flow mechanisms. The studies have been done for the last sort of 30 years. There was a lot of studies that were done in Yucca Mountain, which was a proposed nuclear radioactive disposal site in the US. It was canned, I think, when Barack Obama became president. I think it was that time that they stopped funding and they stopped it, and research into the unsaturated zone kind of dwindled. And then it's really picked up again in the last kind of 5-10 years. So yes, a lot of the mechanisms that we've observed from these previous studies have shown that we get film flow, rivulet flow, and sliding of droplets in fractures within the unsaturated zone. And these are kind of the most important. There are a couple, but these are probably the three most important types of flow mechanisms. And they are very dependent on force interactions between gravity, surface tension, capillary pressure, and viscous forces, and that relationship between adhesion, cohesion, wetting, spreading, and the contact angle. So just like Matthias was talking about between adhesion and cohesion, they play a very important role in how water flows through fractures. The film flow is really a fast flow under tension. So the small scale roughness of fractures are the most important to that, because there's that adhesion to the surface. Droplets, on the other hand, kind of exist as regardless of the wettability. So regardless of whether there's a small scale disparity or not, it's actually held by capillary forces, which is quite weak in large apertures, as we'll see in a couple of later slides in our experiments that we did. But under higher flow rates, rivulets can form. So this image here kind of just shows that relationship between the contact angle. We've got a 0 contact angle up to a contact angle of 180 degrees. Most rock fractures are closer to 0 degrees. We did flow visualization experiments at first using perspex or plexiglass, and that had a contact angle of about 70. So you expect to see droplets and rivulets, and that's where kind of cohesion is slightly higher than adhesion. But in rock fractures, we're looking at closer to 0 degrees, and that's where you get the spreading, between the spreading and adhesion. So you get films, some droplets and rivulets. Adhesion can be greater than cohesion, but it can also not be. So we get a lot of wetting of the fracture and a bit of a hydrophilic response to flow of fluid through the fracture. And obviously those force interactions between gravity and capillarity and the rest can result in complex flow phenomena such as episodic fluxes, intermittent fluxes, and preferential flow paths. And fractures and their subsequent intersections play a dominant role in controlling these phenomena. And these obviously lead to the flow focusing, fast preferential flow, intermittent flow episodes, flow switching, and slender pathway flow, which we kind of can see conceptualized here in this little schematic at the bottom. This image on the left here just shows that relationship between contact angle and flux. So if we're looking at our plexiglass, for instance, plexiglass experiments, which you'll see a bit in a few slides, those were about 75 degrees. So we expected to see sliding droplets at low flow rates, then some rivulets, maybe some wavy film flow and turbulent film flow as we increased our flow rate. But in rock fractures, we really only get sliding droplets and film flow, which are the two most important. We can get rivulets, and then at higher flow rates, we get wavy and turbulent films. But sometimes with the cubic law, which relies on the assumption that there's a linear relationship, and that it's really only valid when inertial forces are kind of negligible compared with the viscous forces. But that's really only anticipated for low flow rates. So the linear Darcy's law is not always suitable to describe flow behavior in fractured rock. And then an increase in flow rate, in which there's an increase in discharge, is smaller than the proportional increase of the pressure gradient. That occurs due to non-negligible inertial losses. You can imagine that happens when there's variations in the geometry, when we have roughness, when we have constrictions, when we have bridging in the fractures or obstructions. It induces inertial losses, and that initiates turbulence. So the cubic law relies on a lot of assumptions, which in nature aren't sort of respected, obviously. So for non-Darcian flow, what we tend to, or the most widely used law, is called Forchheimer's law, and that just essentially describes nonlinear flow by this simple equation, which uses these two coefficients, coefficient A and coefficient B, which are the linear and nonlinear coefficients respectively. And coefficient A is a function of the fluid properties, coefficient B is of the medium geometries. So if you'd expect there to be not any geometrical or roughness parameters that would induce that turbulence, that coefficient returns would become 0. So then you start to get back to the cubic law. So this becomes a linear relationship. So it's really that coefficient B that helps describe nonlinear flow in terms of fracture flow. So just moving on to a couple of the experimental studies. Now we did quite a few, but I've just highlighted some of the more important ones based, on our findings through both applications and to where kind of, Mampho and Duan will obviously expand on some of the more complicated findings. So this was one of the very first experiments we did. It was very simple. We had two smooth parallel plates. There's the plexiglass, and what we did there was we had an inlet. There's the horizontal fracture, so you can kind of see it a little bit schematically presented there in 3 dimensions. So there's the inlet, there's the horizontal fracture, flow then occurred sort of down what is now down the slide. There's the fracture intersection, and there's the vertical fracture. So you can see we introduced the water into the inlet here, flowed along the horizontal fracture and out into the vertical fracture. And what's immediately noticeable there is that we have full saturation in the horizontal fracture, but it's the vertical fracture is variably saturated. That's probably at most 20% at these high flow rates here. So we have these initially dry free draining conditions, even for vertical fractures that are supplied by saturated horizontal fractures. So in this case here, if we extrapolate this to the intermediate fractured Vadose, and the cubic law assumptions are violated, and there's no real proposed alternative, even though we have other equations to describe nonlinear flow. In terms of describing fluxes, it's not that simple. But what about the influence of other properties and parameters, like I'd mentioned, the geometry of the fracture, the roughness, infill, flow rates, intersections, fracture networks. So we started off simple with the aim of starting to increase the complexity in our models. Now what you see here is that you've got this nice saturated horizontal fracture and this variably saturated vertical fracture. Well, how can we describe that relationship? So what happens is that if we plot the vertical saturation against the vertical linear velocity, you can see here if we increase the saturation, so there's an increasing saturation, and what happens is as soon as we have an increasing saturation, so let's just go back here. So in this case here, at this low flow rate, we have this kind of saturation, and we're obviously increasing it as we're increasing the flow rate if we look at this vertical fracture. And what happens here is when we increase that saturation, we actually get a decreasing velocity in that vertical fracture. So that's a function of Bernoulli's law, the continuity principle, essentially, where you increase the vertical velocity as you decrease the degree of saturation. That has to happen to accommodate that amount of fluid flow that is flowing through the fracture. We also did we mimicked some Lugeon or packer tests, water pressure tests on these fractures. We wanted to see what happens in the unsaturated zone when we hypothetically inject it with a packer, with water in the packer test. So this little schematic up here, this diagram kind of shows what we were thinking, where you've got your test zone there, your testing section. There's the packer. You can conceptualize this as a single packer test with the base of the test section intersecting an inclined fracture there. So I was jumping ahead. And what we end up, my animations are a little bit mixed up here, but essentially what we're getting here is an increase in pressure and then a decrease. So there's our P max, our maximum pressure. And you can see even at that stage, or we don't get full saturation of the fracture. What we do see, interestingly though, is that in increasing our pressure, we start to get this decrease in our Lugeon value. Now, if you look to characterize that in any Lugeon interpretation, you assume that that's a nonlinear or a turbulent flow. And we shouldn't get turbulent flow if we have a simple, smooth parallel plate, but we do. And so it's obviously a function of the unsaturated zone itself, of that fracture being variably saturated. So that just shows you there how we've got that increasing pressure between these screenshots, and then we have the decreasing pressure. And you'd have to think, well, if we theoretically should be getting a laminar flow where all of these Lugeon values should be the same, but now we're getting this turbulence, and while we're getting this turbulence, usually in fracture in Lugeon tests, when you see that turbulent flow or nonlinear flow, you start to think about things of the roughness of the fracture, and that sort of guides how you'd characterize your rock mass. If you're looking to grout it, you'd think about your grout mix if you're getting very turbulent flows, because that probably means that your fracture sets are fairly rough, and you've got a very variable aperture. This just plots up what we then did was we plotted up using Forchheimer's law. We looked at what Forchheimer's law would predict the flow rate to be according to the pressure head, and you can see that our measured values in our Lugeon tests for all the tests actually plot fairly well, which means that the Forchheimer's law can most likely be used or might be applicable to fractures in the intermediate fractured Vadose zone. So we saw really good results using that Forchheimer's law. I can see there's just the difference. I've just plotted that to show the linear relationship, and here we can see that non-linear relationship. In terms of Reynolds number really describes the onset of turbulence. In fractures, full turbulence is generally assumed as occurring beyond a Reynolds number of about 2000. But in some instances, we're already seeing turbulence being onset as low as kind of 5, a Reynolds number at 5. But full turbulence kind of is at a much higher Reynolds number when flow rates are higher. This is a few photos from our research colleague Katlego Sekgole, who did a master's in looking at variation of fracture aperture, and that I just wanted to put in here to show you the influence of mechanisms in fractures, and how we get this gravity-driven flow, and here we get capillary-driven flow, and looking at gravity forces dominate towards the left, and capillary forces will dominate towards the right. To kind of finish off, I just wanted to before Mampho really complicates things, I I really wanted to kind of think about some of the contributions and the implications in field applications. So if we look at some of the influence of defect orientation, when we have this saturated horizontal fracture and then we get a change of orientation, which might be regarded as a fracture intersection, if we conceptualize it like that, when we have change to a lower degree of saturation in the vertical flow path, what happens if we go and excavate our tunnel through that portion of that vertical fracture? We won't intersect any water. The rock mass or the tunnel face will be dry. We can go and intersect it there, and then we intersect this discrete flow path. And because there's such a low degree of saturation on this vertical face, we're going to get high inflow rates, because all of that groundwater flow in the horizontal fracture is having to be transported at a low degree of saturation, which means a higher linear velocity in this little flow path. And we can see these type of things in nature. Think about a waterfall where you've got this pooling at the top in that horizontal at the crest above the waterfall. And then what happens when it spills over the crest? You get these nice singular kind of waterfall features. And that's a great example of kind of, or an analogy of how fractures will behave in wider aperture fractures. So what implications do we have for site characterization? If we, like I mentioned with that Lugeon test, if we're looking at a hypothetical discontinuity under saturated conditions, when we do our Lugeon tests, we expect to see some laminar flow. And we should be getting similar Lugeon values. And what would we do in that case? Well, you average the Lugeon values and you get a Lugeon value of X over here. But if we're doing it under partially saturated conditions, like we did in that experiment, and we're starting to see what we describe as a turbulent flow, so at our highest pressure here, we've got the lowest Lugeon number. Well, in that case there, we have to take a lower Lugeon value. It's the same fracture, it's the same rock mass, but we're going to assign two different Lugeon values, and how will that impact how we characterize the rock mass? If we look at the same situation, but just looking at a PQ diagram, a pressure flux diagram, if that's our unsaturated discontinuity, say for a dam site before reservoir impoundment, and we get the fractures and we get this non-linear flow, and then we come along and we build the dam wall and we impound the reservoir, and that fracture becomes saturated, we'll have linear flow occurring hypothetically through that fracture. So again, look at that difference. How are you characterizing your permeabilities from your Lugeon tests? Are you considering the degree of saturation at that time, and how that's going to change over the project life cycle? Just a few nice photos to really finish it off. This was one of our case studies, was De Hoop Dam. Now this is about a kilometer-long dam wall that was built near Steelpoort. It's 80 meters high, it's its tallest over here, and we got a hold of a lot of data along this during the excavation of the foundations. So this whole foundation was mapped. They conducted water pressure tests, Lugeon tests before grouting in the grout holes. So we had all of that, and we were able to really scrutinize that data. And one of the interesting things that we noticed was that obviously as we moved down to the river section where there was a higher degree of saturation because we were closer to the river, we started to see a lot more correlation between all sorts of parameters. Lugeon takes, grout takes, sort of the RQDs, fracture characteristics. There was great correlation between them, but as soon as we moved up into the upper flanks where it was variably or unsaturated even, we saw a chaotic correlation or no correlation at all. So if we just look at this kind of goes from the upper left flank to the lower left flank, middle left flank, and then river section. So this is the wettest portion. And if you just look at this axis, this is a secondary permeability axis, but think of it as this is data from the Lugeon test, which kind of describes a permeability. So there we have a sort of increase in permeability, and sorry, on the y-axis we have grout take. You can kind of see our relationship is very poor. So at class D, where it's a very permeable rock mass, we should be getting high grout takes, and we weren't. But as soon as we got to a wetter zone, we seem to get a better correlation between our Lugeon tests permeabilities and our grout takes. So that was just one kind of flag. Couple more in terms of tunneling here in Sydney. We get these Hawkesbury sandstones that are horizontally bedded, And we see these wonderful horizontal bedding planes that are full of water, and you get these nice flows out of vertical fractures or out of vertical faces. And that has some implications in the tunneling industry, obviously. Here's a great example from one of the tunnels that they're busy constructing at the moment. Look at that beautiful horizontal bedding plane that's there. Everything's dry above it. As soon as that water-filled horizontal fracture spills over into the tunnel, we've got this vertical flow. So where I really want to go with this is start to look at trying to quantify or looking at the contributions of what we've researched here and looking at how we apply it to what we do in our day-to-day. And we started to look at that by understanding how recharge zones can be several hundred meters away, but horizontal fractures transport, saturated horizontal fractures transport this, and then they are intersected either by vertical fractures or tunnel faces where there's a low degree of saturation, but there's a high flow velocity. So it's probably not so great to see in your resolution that's showing on your side there, but there's a quite a large amount of flow coming out of the tunnel face here. A great example, what I think of mine slopes and even more complexity. This is a mine in Papua New Guinea. It's an epithermal gold deposit located on a volcanic island just north of the mainland of Papua New Guinea. It's situated in a caldera that formed about 1 million years ago. So all the blasted material kind of ended up in the ocean. That caldera is still cooling and it contains an active geothermal system. The mine had done some studies to expand the pit out here, but this was an area of thermal upflow where rock temperatures were in excess of kind of 200 degrees. And the best blasting emulsions are unstable at around 100 degrees. So they wanted to look at an idea of cooling the rock mass around here. And one of the ideas was to maybe inject seawater, to pump seawater in and then out again. So this is one of the great studies that there's to look at this and this hydrogeological characterization. So it was all about describing the hydrogeological rock mass model development to support this cooling system to lower the temperatures below 100 degrees Celsius. So it could be mined. This is an example of some of the sort of geothermal, the steam coming out of some of the rock mass there. And really, it involved quite a big study looking at how much connectivity there was in the rock mass units and how we characterized the different rock mass units. So we needed to consider, because it was more of a thermo-hydromechanical coupling scenario where you had variable saturation, you had mechanical properties of your rock mass, and you had this thermal influence. So you didn't want to inject the water into here to cool the rock mass, and then you load it by injecting the water. So you pressurize the slope, and then it's further pressured by the steam, by the geothermal activity. So it was really important to characterize the rock mass and understand where the high permeability zones were. So here in this photo here, you can see there's one of these listric faults. And the fault zone is fairly impermeable. And just adjacent to it's fairly impermeable, as you can see, but just adjacent to it on the distal zones, you have a very impermeable rock mass. You can see that by the steam escaping. So there was a lot of correlation between packet testing data with drilling and mapping to try and understand the influence of fracture connectivity and the fracture system based on defect properties. And it was really this great marriage of looking at borehole data, packet testing in that discrete borehole, as well as mapping data to look at the persistence and continuity. But what about the implications of conducting these Lugeon tests in this sort of variably saturated rock mass with a geothermal component? What about non-linear flow? If you've got this unsaturated rock mass that you are injecting water into and you get linear flow, are you calculating the correct volumes of how much water needs to be injected to cool it to below 100 degrees Celsius? So that was kind of that's the thinking, is to start thinking a bit beyond where we are at the moment in terms of better characterizing our rock mass. So in conclusion, the intermediate fractured Vadose zone, the cubic law assumptions are violated in non-horizontal fracture. There's really been no proposed alternatives. And how water moves through discrete fractures at partial saturation is understated. There's less emphasis on fluxes, but there needs to be more emphasis on variable travel paths that are driven by their linear velocity. And more studies are required to obtain a unified view of preferential flow through fractures, and that allows us to link processes. So finding a suitable representation of a rock mass is very difficult. So we've got to look at the smooth parallel plates and then look at roughness and then look at infill and slowly build up our understanding by separating all these components. But there are preliminary answers to explain flow deviations for commonly applied saturated Darcian-based approaches. And that previous saturated conditions that were assumed or used in calculations are incorrect. And hopefully this research has sort of emphasized how fracturers, the variably saturated conditions and orientation influence flow mechanisms. And we really require deep understanding of small-scale processes that characterize the intermediate fractured Vadose zone. So with that, I'd like to thank you and hand you over to Mampho to increase the complexity even more. Thank you.
Thank you very much, Brendon. We'll take questions afterwards if there's time for that. But while we are now busy with the topic on fracture flow, it makes sense to immediately continue to Mampho. So I hand over to Mampho now. You can just go. Just get there. There you go.
Okay, good afternoon, everyone. Today I'll be talking about variably saturated flow, basically concentrating on the fundamental concepts in natural fractured rocks. So unsaturated or partially saturated flow through natural fractures is a complex topic due to factors affecting water movement in the unsaturated zone. So unsaturated flow through fractured systems affect most engineering works, as Brendon has shown, with underground openings or excavations, as well as the subsurface water cycle. So pore pressure changes in space and time, and moving water...
Please switch off your microphone. Someone's microphone is on. Just go.
Pore pressures change in space and time, and moving water mobilizes and transports a wide possible array of contaminants in developed areas. And how we design infrastructure or systems affecting the greater water cycle inevitably alters the moisture content differently at different places in the subsurface. So previous studies have concentrated on the smooth parallel plate model, and the purpose of these conceptual models was to understand and define elementary methods that govern fluid flow in fractured systems. But partially saturated flow is still poorly understood, and the use of commonly adopted saturated approaches are not always applicable. So the fundamental concepts represented by a set of gears for the unsaturated flow in natural rock fractures follow no particular order, but this figure emphasizes that all these concepts are intertwined, where at first you see the blue here, you have partially saturated flow. Can whoever's mic that is on, please switch it off?
There we go. Mute.
Okay. Okay. Sorry about that. So the fundamental concepts are represented by a set of gears for unsaturated flow in natural rock fractures, which follow no particular order. But the figure places emphasis that all these concepts are intertwined. For the first gear, which is blue, where partially saturated flow through natural fractures is affected by the properties of the geological media, this including your mineral composition. Then your geometrical intricacies, this includes your orientation, aperture, roughness, and stress regime, as well as surface wettability, which refers to a fluid that spreads on the solid surface. in the presence of another fluid, and porosity, whether the water is either stored in the matrix or transmitted through the fracture, which will then ultimately influence the flow mechanisms and regimes. So this presentation will mainly address these concepts, linking it to experimental work to support the research findings. So in order to improve our understanding of partially saturated flow through discrete fractures, falling head tests were conducted. Falling head tests were conducted on shale and quartzite samples at different angles of inclination, in which shale, which is the first picture A, was sought to dimensions of 200 by 155 millimeters, and quartzite, which is B, was sought to dimensions of 225 by 200 millimeters. This was done so that both the rocks fulfill the specifications of a dominant persistent single fracture on all sides of the sample. Water was then introduced into the point source, as you can see in the image, of each sample and exited the fracture under free draining conditions, which is then the outlet fracture. So the conceptual model was based on continuous influx conditions with 4 tests conducted per inclination, namely your horizontal, your 23 degrees, 60 degrees, and your vertical. So in each test, there were 3 distinct phases, namely your initially dry, which was when the rock was initially dry, then your wet, and the re-wetting phase. Then water was topped up after drainage in the initially dry phase to commence to the wet, followed by the re-wetting phase. Then flow meters were used in order to measure the different flow rates. So you had your low flow meter rates, which was at 20 millimeters per minute, and also your high flow meter flow rates, which was at 200 or 500 millimeters per minute. So following the principles of flow, how rock fractures wet to eventually store or transmit water at variable moisture contexts is subject to very small scale influences at mineral surface water molecule level. So the visual observations show that water preferentially flows on the fracture surfaces in the lateral and longitudinal directions. Then the flow mechanisms, which was covered by Dr. Jones, indicate fluid instabilities and rapid infiltration of water under unsaturated conditions. And the advancement of the flow paths, as you can see, from 0 seconds to 16 seconds for the shale, to 61 seconds to 532 seconds, will mainly depend on the fluid mass, its velocity, and angle of inclination. So the changing of orientations determine the relationship between adhesion, which whether your side walls will be wetted, and cohesion, whether you have attraction of water molecules to each other, resulting in gravitation. So a fluid in both the samples in the direction of the gravitational potential, or as water flows along the fracture, gravity will destabilize it and the fluid will gravitate vertically downwards. So this demonstrates that there is less capillarity and more gravitational drainage in both the samples for all angles of inclination. So keeping in mind that falling head tests were conducted, hydraulic gradients still dictate flow under high enough water or moisture contents. But at low values, orientations of fracture walls may dictate the direction of water movement rather than gravity alone. So following the initially dry phase, fluid flow in the wetting and the re-wetting phase forms new flow paths, or the pre-existing wetted flow paths from the initially dry phase. So as a result, the flow paths either merged, they widened, or there was an increase in the dispersion of the wetting front. So then this brings us to that variation in surface morphologies may create regions with lower wetting resistance, where the fluid deviates from the flow path. Then contact obstacles delayed the flow path length, hence water drained faster, traveling in straight lines in larger surface areas with minimal contact points. So the geometry of rock fractures will affect fluid flow due to a change in aperture, roughness, and contact obstacles. So, for example, in South Africa, most of the developed nodes are underlain by fairly shallow fractured bedrock with regional groundwater levels generally below the bedrock surface. So this will require an enhanced diligence in understanding what will happen when draining wet rock or when wetting dry rock. Because as developments go deeper, should the design not adequately address the altering subsurface cycles, the consequences will become more threatening. So fractured rocks also behave as a double porosity medium. So porosity of a medium is quantified by the volume V, as you can see, volume under investigation. So with an increasing V, porosity fluctuates and generally stabilizes in a range where the porosity remains constant over a certain representative elementary volume. So as represented in the figure, the REV becomes important when modeling for natural fractured systems. So in this case, we were modeling for single discrete fracture. So the different scale of investigation will result in the rock mass being considered as a porous medium. So for example, if two similar natural fractures without any random pore heterogeneousness are under investigation, the porosity will be the same. But if the volume of scale of one sample is extended, the porosity may change based on the microscopic and the macroscopic heterogeneities. So from our experiment, we know that despite the minerals present in the rocks having different wetting properties, imbibition into the primary pore spaces plays a dominant role, implying a double porosity system where the shale was more porous than the quartzite. And when flow occurs through fractures, at some moisture threshold, infiltration into the interstitial porosity occurs, which will result in low discharge rates affecting the flow regime. So when investigating flow visualizations within fractured systems, we should also consider exactly what happens in the fracture, what is the flow mechanism, and what is the flow regime, and not only concentrate on water budgets. This is difficult to determine as a rock is not translucent, but we know that flow mechanisms and regimes are mainly affected by the geometry of the rock. So in our experiments, we incorporated the hydraulic roughness, which is described by the relative roughness. So the relative roughness is related to the Reynolds numbers, as mentioned before, in which the Reynolds numbers indicates the flow regime, whether your flow will be laminar or turbulent. And in addition to this, the flow regime may be described further, including rotationality. So we account for frictional losses of the streamlines through the natural rock defects. So as you can see in the picture, you have irrotational flow, and you also have rotational flow. So instead of just saying flow is just turbulent based on the discharge rates, we now look at the streamlines and say turbulent irrotational flow. So the hydraulic roughness also considers the aperture of the fracture in the bottom picture. This is because aperture generates open space for flow to occur. So with increasing aperture, gravitational forces start dominating over capillary forces as there is proportionally less surface available. So aperture will not only reduce the shear strength of the rock, but it will also promote hydraulic connectivity. So this is the results from our experiment, in which the first table shows the average range of the Reynolds numbers for both the samples, which indicate turbulent failure. So there is also a lag between the cumulative discharge rates for water inflow, denoted as Q in, and water outflow, denoted as Q out, representing the wetting of the fracture. So this inevitably affects the Reynolds numbers of the outflow, which are lower than the inflow of the Reynolds numbers. There's also, in the last table, there is also a significant Reynolds number percentage change for the shale and the quartzite, indicating porosity. So the bottom table indicates the results of the average aperture of each fracture in the lateral and the longitudinal directions. The fracture walls are then classified as hydraulically rough, looking at the streamlines, because these results indicate rotational flow where relative roughness ratios are greater than 0.32. So we are not only describing the flow as turbulent or laminar, but also hydraulically describing the streamlines within the rock. So moving on to our recent research, we are also looking at truncation bias in fractured systems. We know that characterization of rock mass properties is necessary in the determination of its geometrical and its hydromechanical behavior. So sampling errors can be in terms of misrepresentation, for example, where outcrops are disturbed and do not reflect the actual conditions, or where measurements are variable based on the scale of measurements, like in the figure showed. So at first you could map where you have increased weathering and erosion of structures exposed on surface, or you can have a decrease of decomposition due to more stable environmental conditions, or the rock block not in the true orientation, resulting in changes of strike and dip, which will ultimately affect your results. So orientation of data of fractures are biased based on the collection technique. So borehole core or outcrop scan line mapping apply a linear sampling technique, implying that the statistical methods are often used to reduce the bias. However, this will require fractures to be exposed and present along the trace length, in which for truncation bias, some of these fractures are not accessible. So these results may be affected greatly because stress changes in the rock mass will either increase or decrease the aperture width and cause a change in permeability. Then this will affect your discharge rates, influence the distribution of the hydraulic head, and affect the seepage forces acting on the rock mass. So this highlights sensitivity of field measurements and understanding that roughness influences not only the flow rate, but the distribution of moisture in defects. So as part of our experiments, from our lab experiments, we already know that the estimation of the two-dimensional JRC, which is your joint roughness conditions, coefficient, need further refinement to more accurately estimate the effects of geometric controls. Therefore, the determination of roughness in joint line survey data should reflect the section along the joint that will have the biggest influence on flow. This is because joint roughness is one of the characteristics that needs careful quantification as it governs the shear strength of discontinuities within a rock mass and its stability. So then small-scale roughness of joint walls were reviewed in great detail through a three-dimensional sampling approach that involves the use of circular discs of different dimensions, which is then your 50 millimeters, 100, 200, and 400 millimeters. The discs were employed together with the geological compass to take joint orientation readings along the joint planes of the slope. So then the readings recorded at similar points displayed variation owing to the asperities of the joint surface and the size of the disc used. So this approach results in a representative orientation of the discontinuity planes due to an enormous amount of data that is collected on the same plane. So from this research, we learned that the amplitude and the wavelength measurements obtained are not incorrect, but rather the empirical equation that we're currently using for JRC needs some altering on the scale measurements in order to accommodate for the lengths measured between your different contact points, which have effects on your flow visualizations, and not only the scale length in which it is derived. So a lot of work is still needed to be done, and also incorporating model techniques, as this determination will enable us to understand the mechanical and hydraulic behavior of rock mass better. So in conclusion, insight into unsaturated flow through discrete natural rock fractures, this is aid to improve our understanding of groundwater recharge and contamination, reduction in shear strength of wet fractures in rock mass, and possible solutions to the drainage of rock slopes and excavations. So in order to truly understand the influence of fracture geometry on flow, more complex experimental work entailing different aperture, roughness, and infill will be beneficial. So as our way forward, we need to upscale to the field level, which is what we are currently doing, and then also incorporate more complex systems. That includes then your case studies in order to relate it to real life problems. Thank you. I just thought I should show my face.
Thank you very much, Mampho. We continue now with the last one. I will look whether there are questions or not, but I think it's going really well. So our last one is now Duan Swart. And I'm just immediately going to hand over to Duan. Thank you so much.
Good afternoon, everyone. Thank you for making time to come listen to our talks. I'll be talking today about just basic unsaturated soil mechanics, and this forms part of my PhD studies at the University of Pretoria. This is a basic representation of a deeply weathered soil profile with the water table shown by the blue line at the bottom of the slide. The pore water pressure distribution is shown by the green line and is linear, representing hydrostatic conditions with zero moisture flux at the ground surface. The soil moisture distribution under the same conditions will be nonlinear and represents two distinct points, namely the air entry value and the residual suction. These 2 points subdivide the Vadose zone into 3 subsections, starting with the capillary fringe or zone, where the soil is virtually saturated, the 2-phase zone, where air and water is continuous in the pores, and the dry zone, where water exists as films around soil grains and only air is continuous in the pores. In reality, the hydrostatic conditions exist when the ground surface is sealed by either pavements, foundations, or thick soil crusting. When the climate is arid and soil is bare, there will be a net moisture loss and a general upward movement of water, and a greater negative pore water pressures will exist. This condition can also occur if numerous eucalyptus trees or gum trees are present. Going the other way, where infiltration by precipitating water causes a net moisture increase and a downward movement of soil moisture, and lesser negative pore pressures will exist. In a special case, flooding of desiccated soil or an open excavation may cause the pore water pressure to tend to zero and saturated conditions. The changes in the pore water pressures occur in the upper portion of the profile known as the active zone. So how do we describe Vadose zone or unsaturated soil mechanics stress states? To put into context, saturated soil is explained by using effective stress, which is the total stress minus the pore water pressure. For unsaturated soils, 2 independent stress variables are needed. These are matrix suction, which is equal to pore air pressure minus pore water pressure, and net normal stress, which is sigma minus pore air pressure. 2 stress state descriptors are needed for unsaturated soil because a change in pore water pressure does not produce the same change in the soil as a change in normal stress. We characterize the soil with the soil water characteristic curve. The water content is on the y-axis and the log of suction is on the x-axis. We developed this graph by measuring the suction values by using a high capacity tensiometer while a saturated soil dries out. Looking at how a soil dries out on the left-hand side of the slide, the soil is virtually saturated until the air entry value is reached. This point represents the value that breaks the meniscus of pore water in larger pores of the soil. Continuing to dry out, the soil is made up of 4 phases: the soil particle, the pore air, the pore water, and the contractile skin. This skin is formed by a web of menisci due to the surface tension of water films between the grains. The pressure difference across this contractile skin is the matrix suction. When this pressure difference increases, or in other words, matrix suction increases, the contractile skin needs to stay in equilibrium by tightening along the surface tension. This is how unsaturated sandy soils gain apparent cohesion. The soil water characteristic curve is used to estimate or predict unsaturated soil property functions and behavior of unsaturated soils. The unsaturated soil's property functions are seepage, volume, and shear strength. These are all influenced by changes of moisture in the soil. And I'm sure most of you have dealt with volume change problems, be it swelling or collapsing soils, or shear strength problems. So today I'll just be discussing seepage, also known as the permeability function of unsaturated soils. The permeability function is predicted using the saturated coefficient of the permeability and the soil water characteristic curves. Flow through unsaturated soils can be put into one sentence. Water can only flow where there is water. This is also represented by the graph on the right. Though this graph only applies for soils that stay intact. For example, a desiccated soil will have a high coefficient of permeability through cracks compared to the matrix permeability. In unsaturated soil, Darcy law still applies, but the coefficient of permeability is not a constant anymore, but a variable that's dependent on matrix suction. To show this, here we have 2 soil water characteristic curves, one of a fine-grained soil and one of a coarse-grained soil. From this, we predict the permeability function. The saturated permeability is maintained until the air entry value is reached. As you can see, the fine-grained soil has a much higher air entry value as the coarse grained soil. So the permeability, the saturated permeability of the fine grained soil will maintain for longer. An interesting note, or after the air entry value, the permeability function decreases as suctions increase. An interesting note to make here is that at a certain suction, clay can have a higher coefficient of permeability than sand. Matrix suction, or should I rather say the unsaturated soil property functions are dependent on matrix suction, and the matrix suction exhibits hysteresis during wetting and drying cycles. Therefore, the unsaturated soil property functions also exhibit hysteresis. The soil water characteristic curve represents a family of curves. When measuring suctions of a drying sample, the drying curve is produced. If the suctions are measured of a wetting sample from a dry state, the wetting curve is produced. These two curves represent, but not always, the boundary of all possible curves. For example, say you have a soil that is drying on the drying curve and conditions change, causing soil moisture to increase. It may follow this curve. In another example, say a wetting soil starts to dry, say there's a wetting soil that starts to dry, the conditions change, it starts to dry, and then it may follow this curve. But then again, the conditions could change and the soil could start wetting up again. So it could loop around like this. These are called scanning curves, and there's an infinite amount of curves possible in between these two main curves. Where the soil suctions lie on or within these two boundary curves, this will have an impact on the soil water property functions, and it could impact the permeability by orders of magnitude. Hysteresis happens due to during the wetting and drying of soil, the pores empty out in a different order than what they fill up, and an advancing meniscus has a different shape to a receding one. Air can also be trapped during a wetting process, and the geometry of connecting pores also play a role in this. As spoken on the first slide, the condition at the boundary surface has a major impact on the pore water pressure distribution of the profile. By altering the boundary conditions, the ground surface moisture flux will change. Regionally, this may happen through climate change. Even though this is a natural process, research has shown that humans are aiding in this. So much so that we've reached the Anthropocene. Scientists say South Africa will experience a 3 to 6 degrees Celsius increase in average air temperatures in the next 100 years. Rainfall is more difficult to predict, but scientists say that wet areas will get wetter and dry areas drier. Evaporation is expected to increase, with similar amounts of rainfall expected in some areas, but the rain will be distributed during only more intense rainfall events. You can imagine how this overall effect will affect the soil moisture. Locally, humans have a direct impact on the ground surface, be it through most developments, farming, mining, building dams, etc. To show how humans can impact the pore water pressure profile, I'll quickly run you through an example. Here we are in the Northern Cape. It's arid climate, dry soils, high matrix suctions. Developer comes along and says he wants to build a golf course with an eco estate. This will change the moisture distribution, consequently the suctions, whereby changing the unsaturated soil property functions. These changes will impact the movement of pollutants in the soil, the groundwater vulnerability, and slope stability of parts of this development of built-on slopes. How water flows through the Vadose zone is an important part of this research. Here are some inferred flow scenarios. In the Vadose zone, water movement is not only governed by gravity, but rather water can be held under suctions above a capillary barrier or be mobile under hydraulic gradients. The impact that anthropogenic activities will have on these flows is what we'll look at going forward. What we looked at so far is the study of residual dolomite and WOD. Here's the soil water characteristic curve of a structured WOD sample and a remolded sample of the same material. This is what it looked like in the field, and here are some of its properties. It's mainly a salty material with a high liquid limit and a low plasticity index. It was mainly composed of manganese oxide, followed by iron oxides and some silica. The high liquid limit was due to the fine grading of the soil, the microscopic structure of the manganese oxides, namely bursonite, and the ability for water to attach to the oxide surfaces through adhesion. In structured form, the material had a dry density of 309 kilograms per meter cubed, and at the saturated state, it was able to have a water content of 300%. Looking at the soil water characteristic curves, the structured wad has a much higher air entry value than the remolded sample. This is due to the distribution of smaller interconnected pore spaces provided by the inherent structure in the wad material. This structure contributes to the high water holding capacity of wad as well. Here, it's the same sample. It's a soil electron microscope image at 500 degrees magnification of the structured wad sample. In this image, we see a matrix of silt grains with a few clay particles here and there, and a large quartz grain. Notice the difference in pore distribution around the quartz grain and the silt size grains. Going forward, we'll be completing studies looking at unsaturated soil properties of low plasticity silty residual soils in different climates in South Africa. With these samples, we'll be developing soil water characteristic curves, determining their unsaturated soil property functions, and looking at the chemical makeups of these soils. We would also like to join up and work with the work done in hydrogeology to try to help quantify the qualitative work done there. And lastly, we will be developing and quantifying more of the infinite flow scenarios. If you're interested in any further reading in the subject, here are some good references. These are my references. And this is just an example as to where someone didn't take unsaturated soil mechanics seriously. This is a slow failure during the rainy season last year in KwaZulu-Natal. The image doesn't really do it justice, but the blue oval is where a part of the foundation used to be. And then the blue arrows show some pluckies and the bowl. The whole house just got washed away from the landslide. Thank you so much for listening, everyone.
Good afternoon, everyone. We ran a little bit over time, but I hope you found it interesting what we are busy with at the University of Pretoria. I think it's this magic link between the mechanical properties of soils and rocks and the interaction with the water environment, with the flow of water, and especially the unsaturated flow. And I hope you've found it interesting, and thanks to Dr. Jones, Brendon, and Mampho and Duan, who shared their research with us. While the whole presentation has been recorded, I think there will be communication with you guys if you want to have a look at that again. Thanks to Matthijs for really starting this all. And I don't think we really have time for questions. So it's really just wrapping this up. So thanks very much for signing up. We will probably in the future repeat this with other research that we are busy with at University of Pretoria. And I think, again, as Vadose actually mentioned, we want to really thank the Water Research Commission for supporting research at University of Pretoria in geology, and also having the far-sightedness to actually see the link between the mechanical properties, the water environment, and what this will actually do in future if we look at climate change and how we actually need to look at, well, the groundwater resources, but also the infrastructure development that links up to that. Matthijs, I don't know whether you want to add something to that. Thanks.
Thank you, everyone. So I see there are a few questions. Those of you who want to leave, you're most welcome. I will also share this. There's a few questions here that I think maybe, I don't know I see about vertical flow from horizontal. I think what we will do is we will copy these questions, and then please just find us on the SAIC or the groundwater division site, or you all have my contact details. And I promise you that we will have a response to these questions ready with the recording. You all have my details.
I'll respond to that first question from Carrie quickly.
Great, go for it, Brendon.
Yes, we did look at vertical flow into a closed system. So we did have a vertically closed fracture there. Results were very similar. What we didn't do was start to narrow that aperture. So the results always favored gravitational forces. So obviously, as soon as you close the aperture or narrow the aperture, you will start to get more capillary forces dominating. But yes, we did consider a closed fracture, but it was still a fairly open fracture in terms of the aperture width. So yes, we did, but there's still a lot more work to be done in terms of looking at tighter apertures. Matthias, I think you're on mute.
So maybe just quickly to just finalize this one person's questions, asking Mampho about whether the lab test used only one of each and whether there was comparisons. Yes, she did compare them. That's in a separate paper, a bit too much for this quick talk today. And yes, she is upscaling to the actual field and other rock types now, even looking into double porosity systems. And then Duan, regarding the plant-soil interactions, have you been able to conceptualize potential for specific variability due to plant types? No, we've specifically up to now excluded evapotranspiration as a variable, and we specifically only looked at the composition of a collapsed residual soil. More on that later. We will give you feedback on all of this. It's really appreciated to know that everyone cares about our research, and please keep track. All the best. Goodbye.